All right. Good afternoon, or good morning, or good evening, or wherever you are, or whenever you are watching this. Today we're going to be talking about some simple mechanisms. This is, again, a high-level overview, and we're going to be talking about 2D load analysis with an example. Okay. And so we'll talk about 4 degrees. We'll talk about degrees of freedom first, types of mechanisms, some 4-bar mechanisms, and then some statics review, and then an example with EES. Okay, so mechanisms are everywhere. These are all 4-bar mechanisms. The bike actually is a 4-bar mechanism if you treat your hip as a socket. This is a 4-bar mechanism here with the bottom of this link. If we add some shape on top of it, we can get nice profiles. This is used in all sorts of machinery, especially back before we had affordable and widespread use of servos, which has replaced a lot of the cam systems. The familiar vice grip is a 4-bar mechanism. This is a moray eel. It has a 4-bar mechanism-like action in its jaw when it clamps for high clamping forces. And of course, your toggle clamp is a 4-bar mechanism. This is the ground, this is a link, this is a link, and that's a link here. So you can get nice motion out of these. These mechanisms are used everywhere, from car seats, car hoods, windows, etc. So we don't have the time to go through all the kinematic and kinetic analysis of mechanisms, but at least we can sort of introduce the grammar. It's in the book. I think it's important. It's something that if you are designing machines, you'll probably end up needing or using. So we'll just go over it at a high level view. Mechanisms are composed of links and nodes. A binary link has 2 nodes. A ternary link has 3 nodes, and a quaternary link has 4 nodes. Okay, so the number of nodes defines the link. So these are joint types, not link types, but joint types. We have the revolute joint, where we have a single degree of freedom, where it can spin all the way around this pin joint here. This is a full joint. This is a prismatic joint. Okay, we have 1 degree of freedom, can slide back and forth. This is a pin and slot joint. This is called a half joint. Okay, because this joint can also move in this direction and rotate. It's a 2 degree of freedom mechanism. Link against the plane. This is 2 degrees of freedom, assuming we can't push it in this direction, but that it can slide on its surface and rotate. This is a 2 degree of freedom cylindric joint, so we can spin it and we can move it in the X direction back and forth. So we have 2 degrees of freedom. This is a helical joint, has 1 degree of freedom because the screw motion is coupled to the twist. Okay, so it is actually a helical screw, so you only have 1 degree of freedom, assuming that you have a tight fit, obviously, between the where you're screwing it in, or what you're using as a collar to screw. Then we have spherical joints. They're fixed in X, Y, and Z, but can rotate about the angles for rotate about the X, Y, and Z axes. This is a 3 degree of freedom joint. And then we have planar joints here, which can move in X and Y and spin. So this is just a high level overview of a taxonomy of different joints that commonly show up in machines. So often what we need to know is the degree of freedom of the system, so we can use the Kutzbach equation. And the Kutzbach equation predicts the degree of freedom of an assembly. However, there are some caveats because in some cases it doesn't predict reality. We'll talk about a couple of those here. M is the degree of freedom or degree of mobility. That's why we have M there. L is the number of links. J1 is the number of full or 1 degree of freedom joints. Don't think full joints as in 6 degrees of freedom, but a full joint would be a full pin joint that can revolve all the way around the pin. And J2 is a number of half joints, and that would be sort of like the slider. So you go back here, this is a half joint. Okay, this is a full joint. Doesn't seem intuitive to me, but that's the language. And so J1 is the number of full joints, J2 is the number of half joints. And so using this equation, the Kutzbach equation, we can determine what the degree of freedom is of the system. And I screwed up my slide here. Okay. So this is how we would use it. So this is the Kutzbach paradox. So in this case, we have a structure that has a Kutzbach equation. Okay, so we have 3 times the number of links. Actually, it's times the number of joints. Okay, L is the number of links, so 3 times the number of links. In this case, we have 1, 2, 3, 4, 5 is ground, minus 1, and then minus 2 times the number of full joints. Okay, J1, that's the number of full joints, minus J2, which is the number of half joints. We don't have any half joints, so that's 0. We have 1, 2, 3, 4, 5, 6. Okay, so we have 6 full joints, 5 links, if we include ground. Okay, so this Kutzbach paradox says that, okay, the degree of mobility is 0, and obviously we can look at this and see, this is probably not going to move. But the caveat is, in some cases, if you have a parallel mechanism where you have equal lengths, such as we have here, you can still get parallel motion. This whole thing can actually rotate. Just this is a way of predicting if we have motion, but there is this caveat that sometimes it's untrue. Okay. The 4-bar linkage is one of the most common linkages used in mechanism. In fact, it's the building block for more complicated mechanisms. And I just want to introduce you to some of the terminology. Okay, so in a 4-bar linkage, there's a Grashof criterion for a full rotation. So if you have this equation here, this is your Grashof criterion, and it says if the shortest length plus the longest length link is less than or equal to the other lengths, and in this case there's 4, because we have a 4-bar mechanism, and often that 4th bar is the ground. Okay, so this says if this inequality is true, then the shortest link can be a crank and have full revolution. Okay, if it's false, then no link can make a revolution, and it's not a Grashof linkage. Okay, if they're equal, it's a special case where it's a change point, not a charge point, but a change point, where the positions are undefined. So and a change point is basically where a mechanism, you don't know where it's going to go once it moves from that point. Okay, because there's 2 paths that the mechanism could go. Note that the ground link in a 4-bar mechanism has to be included, and the ground link is always link 1. Okay, the input, which is usually what we attach a motor to, is always link 2. The coupler, which goes from 2 to 3, is always 3. And then the rocker, the output link, which is the desired motion often that you're trying to get, is the output. So that's the terminology. So this is a crank. This is a Grashof linkage because this can go all the way around. Okay, this is the same linkage inverted here. Okay, and we have a different motion. Okay, this is a double crank. So if we rotate this, then this guy can go all the way around. All of the bars can go all the way around. In this case here, the shortest link is actually this coupler. And although if you rotated, this coupler would spin around, you can't actually physically realize that motion usually. I mean, it's very difficult to implement in real life. Okay. So there's some special cases, which we said. There's the parallelogram mechanism, but the motion in this mechanism, which can be really good for like lifting things up and down, is undefined when all the links are collinear. Okay, so one way of avoiding that uncertainty is to prevent motion through when they become collinear, or to add a ternary link in there and then offset the grounds so that you can get full rotation around each of the cranks if you need it. So those are the basic grammar of mechanisms. You've seen them everywhere. This is a non-Grashof 4-bar mechanism in your automotive suspension. It's common design, but it's not really a Grashof mechanism because none of them can complete a full revolution. However, in a car frame, you really don't want your wheel to have a full revolution, so you can strain that motion with the spring and your joints for the vehicle. And so you get small angle rotation about the frame, and you have a very nice suspension ability to take road inputs. Okay, and you see the 4-bar is here, between here, here, and here. Okay, so you have 2 4-bars. In this case, we just have these small rotations. In fact, if you extend the rocker arm, which is the output arm, to infinity, you just kind of keep making that 4th link longer and longer and longer and longer and longer. Well, if you make it infinite, then the grounds are still connected somehow at an infinity. You still have your input crank, but in this case, the output becomes a slider. Okay, so this is the working principle of an internal combustion engine. So you need to have a motor input to keep it to going through the collinear points. Okay, but often we will put a driver here. For the internal combustion engine, it's not a crank slider, but a slider crank because the slider drives the crank. Again, we have the same situation where the 4th bar here goes off to infinity, but the internal combustion from the engine causes it to rotate, and then the inertia from the engine keeps it coming back around to compress the gas and repeat the cycle. But it's kind of interesting to think about, this internal combustion engineering as a 4-bar mechanism. Okay. There's other mechanisms that are, if you take a snapshot in time, actually are 4-bar mechanisms. These are some examples of cam and followers. Okay, so this is a cam on a linear follower over here on the left. So if you take a snapshot in time, and then you take the instantaneous curvature of the cam here, so that would be this curvature from this contact point, which would map out this circle. Then you can take the center of the circle, and then you can imagine a link from the center of the circle to the center of the cam to infinity, and then to the center of rotation of the cam, and then off to infinity. And this is sort of like a parallel link for this entire mechanism. And there's books that are dedicated to looking at the dynamics and the kinetics and the kinematics of these mechanisms. There's some classes such as kinematics that are offered at some universities, and they go into the analysis of this. It's beyond the scope of this class, so we'll stop here. But Norton also has written a book called Design of Machinery, not machine design, but design of machinery, where he does the motion analysis for these types of mechanisms. All right. So there are other common mechanisms you might hear of are 6-bar mechanisms, which is the Watt and the Stevenson. Okay, so take a advanced dynamics class or kinematics class, or get yourself the Design of Machinery book if you're interested. Yeah. All right. So in the book, he introduces a way of analyzing the position, acceleration, and velocity. So we're not going to go in that, but should you need to come back to that, you can actually represent these links for the four bars in terms of polar coordinates. So you can represent this as a vector, a complex vector, another complex vector, another complex vector, and another complex vector. And if you sum these vector sums, they sum to 0. And so if you do that and you represent these in complex form, you can use polar notation, and it actually makes the taking the derivatives easy because you have these exponential terms. So when you take the derivative, you get the exponent brought down times the exponential function again, which is pretty easy to differentiate. So that's what it does in the book. This is just a review of your polar and complex numbers. All right, so if you have a complex vector z, which is represented by x, which is just some value in the x direction, and then some value y in the j direction. This is your imaginary axis. Okay, so we can then represent this vector in the complex plane. Okay, and j here, or I, depending on what you use, is the complex number, which is the square root of -1, which is undefined, or it's defined by j. We have the magnitude, which is the real squared plus the imaginary part squared. We have the phase, which is the inverse tangent of the imaginary part over the real part. We can put it in polar form, which is z, which is equal to x plus j y, or we can put it in this type of polar form, or we can put it in the form that he uses in the book, where we have a vector RA. We take r as the magnitude of RA, and we can multiply it by ej theta. So it's a compact way of representing this vector. And if you take these vectors, you can sum them through the linkages, and then you can take the derivatives and find the accelerations, velocities, angular velocities, and angular accelerations for these. And you can analyze them for your 4-bar mechanism, your crank and slider, or slider crank, and other mechanisms as well. What's interesting is if you use this approach, every time you multiply it by j, you're actually rotating at 90 degrees. So if you have this vector here, RA, you multiply it by j, then it becomes the same magnitude vector, except now it has this j on it, so it's in the imaginary axis. Multiply it again by j, and then you have a -1r, okay, which rotates it again by 90 degrees. And then if you multiply it by j again, you get a -jr, so you're rotating it again by 90 degrees. Okay, so if you use the real and imaginary axes for representing these complex vectors, which represent each one of the links, then it's a way for you to simplify the analysis for that. So we're not going to go through those details. I debated on whether we would do that in this class, but instead I elected to just take a high-level view, introduce you to it, let you know some of the grammar. And should you wish to get into mechanisms or mechanism designs where you require this math, just remember that, hey, we talked about it briefly, and hopefully you'll have this as a reference to go back to. All right. So the rest of this lecture, we're going to go through the load analysis, and we're going to go through an example. Okay. I'm going to summarize 2 entire courses that you took. Statics, the sum of forces and the sum of moments is 0. In the 2D case, we usually use sum of forces in x and y are 0. Sum of moments are 0. 3D statics, the sum of forces in all 3 directions, if we were using Cartesian coordinates, is 0. And the sum of moments about x, about y, and about z are also 0. So that's pretty much how those are the main equations that we learned in statics. Okay, we also had to calculate the mass moment of inertia and different cross-sectional properties and things like that, which are important. But essentially, this is the whole class was, hey, can you sum forces to 0? Can you make a free body diagram? And can you resolve those forces properly? In mechanics of materials, we take those forces and we find out what the stresses are in the material. In machine design, we assume that you already know this. So we're just briefly talking about it here. If we talk about dynamics and three-dimensional dynamics in the Cartesian form, we have the sum of forces is the mass times the acceleration, which is Newton's second law. Newton actually didn't say the sum of forces are the mass times the acceleration. He actually said the sum of forces are equal to the time rate of change of momentum, which is m times v, but the mass is usually constant, so we usually write it sum of forces is the mass times acceleration. Okay, and then we have in 2 dimensions the sum of moments about z is equal to iz, where iz is the principal centroidal mass moment of inertia, or the second moment of mass, and alpha is the angular acceleration in radians per second squared. Our 3D dynamics, we have the same thing. Sum of forces equal to the mass times acceleration. Sum of moments is equal to I alpha, or in this case, the time rate of change of angular momentum, which is actually a more accurate representation of Newton's second law, but we usually write it as Ig alpha. Okay, we can sum forces in all directions and find their accelerations. If we sum moments, okay, we can find that these are the Euler equations, which represent how we find the three-dimensional moments on an object based upon the accelerations and angular accelerations and velocities relative to the distribution of mass around that object. Okay, so there's advanced dynamics classes that you can take here at UNCC. There's a lot to study and in different coordinate frames as well. Of course, this is all assuming a Cartesian coordinate frame. We can have cylindrical coordinates, path coordinates, spherical coordinates, and what have you. Okay, so we need to be able to sum forces to zero to look at our static cases, and we also have to consider the dynamics when we are designing machines that are moving. Okay, we often start with the dynamic case and then move on to the dynamic case. Okay, so this is actually a case study in your machine design book. I think it's case study 3A, and in this case study is just to analyze the brake lever mechanism, and it looks pretty simple, and we follow the pattern to solve this problem just like we did in statics, where we break the bodies up. So we would take this brake lever off, we would take the cable off, and then we would take this bottom part here labeled 1, and 1 would be this entire assembly here because it's all connected. The cable you see goes through the assembly. We're going to assume that there's very little friction in here so that we're not applying much of a load for the cable, and that there's this small angle here of this pin for these loads, which gives us some small Y component as well. Now we cut the handlebar here at some arbitrary point, okay, and when we cut it, we can assume that there's a moment here because we have some load over here and a load over here, and we can assume that there's some reaction forces called Px and Py. Okay, so this is actually a pretty simple mechanism, and I want to show you today kind of just how these simple mechanisms can take some time to analyze, and how important bookkeeping is, and how important software is to support your process. And so I'm going to take this break and we're going to put it in EES, and I'm going to show you how to do that. Okay. Now these are the free body diagrams. Okay. And in this case, we chose some centroid in 2-dimensional case. I think this can be some arbitrary centroid for this thing. As long as we sum the moments properly around the same point, we'll get the right answer. And we can look at this situation here, and we know that this thing is not accelerating, so the sum of forces have to be 0. And we can create a vector diagram for the brake lever here, okay, which says that F32 minus FB2 is F12, okay, the magnitude. And so in this case, we can break these up. We can look at these forces, and we have this force in the cable. We have this reaction force here that comes down from the handle because we're moving it. So we have to have some reaction here that's inside of the arm. And that is counterbalanced by F3(1). Okay, and we can assume that this angle is about 2 degrees, so we can get some expressions for that. All right, so these are the three bodies: the handle, the cable, and the base frame for this analysis. Okay, so I'm going to do this in an EES example. Okay, and so EES I have put on Canvas, and you can download it. Okay, these are the files that I've put on Canvas. There's the documentation. I'm going to walk you through the setup here. You can just double click. And if you double click, you might get this. Yes. Install. Okay. So it says here, installation process. Yes. Agree. Next. Okay. This wants to install it in EES 32, so keep track of that. Okay. And you can install the libraries. This is widely used for heat transfer. Okay. So we're installing. It takes pretty much no time to install. They tell us, hey, installation is complete. So that's fantastic. So then we can go to our EES folder. In this case, we said downloaded it to EES install. And then the last step that we have to do is take the file, okay, from the folder, okay, that I gave you. Okay, notice here that we don't have this EES DFT. We have this EES DFT, whatever that is. You need to take this file and then move it into here. Okay. And then, oh, I moved it. I wanted to copy it. Sorry. Make sure you put it in there. And that's your license file. Now, the last step for you to be able to run EES, you might want to take this and, create a shortcut. There's your shortcut. You can go then to your desktop. Okay, paste your shortcut on your desktop if that's what you want to do. And then the last thing to do is to log into the VPN client for the university. Okay, and that's the Cisco Anywhere client. I sent you the link. Okay, so after you install it, you're going to get something like this. You hit connect. It's going to try to connect. You're going to enter your credentials. Okay, after you get your credentials, depending on what you have, you might get a notification on your phone. So you got to approve it. So after you approve it, you should get it, see that it logs in there. Okay, so here we're connected. And now that we're connected, we should be able to then go run EES. Okay, so to load, continue. If you don't have your VPN, you'll get an error here when you try to run it. So we'll run this. Okay, it ran. If I say A equals 2, B equals 3, then I can say A plus B plus C equals 5. I don't know what C is, but I have here, I can check it. I have 3 equations and 3 variables, no syntax errors. I can check my units. I haven't added units here. If you want to add units, you can. Okay. Let me make this a little, let me see if I can zoom in here. Make this a little bit bigger for you. Let's see here. Probably preferences. Okay. So options. Okay, you can pick your unit system. This is small. Let me see if I can make this bigger. If not, I'll have to zoom in. Okay. Let's see here. Hopefully you can see this on the screen. Okay, so if you want to make the font bigger here, you can make the font big. Hit OK. Now we have a little bit bigger font so we can see it. So as you can see here, we have 3 equations and 3 unknowns, so it should solve. We can check the units. There's no units problems detected, and that's because we haven't assigned any unit. And then we can hit solve, and we find that C is 0. So we can, play around with these numbers, make it -12, solve it again, and now C is 15. So the beauty of EES is you can just write out your equations and then run it. Okay, and another beauty is if we have we can define units. So we say we have millimeters, and then we are entering a bunch of information, and we have meters down here, and we don't define these, and then we check our units. We say the units of A and B differ by a factor of 1,000. Okay, so this is very, very useful in engineering equations. You can go in and change this, or you can do a convert function. Okay, so if we wanted to solve this, we can take a look, we can run it. Okay, 5 equations, no variables, we get a problem. So I added this x here. So if we have this equation and we want to check 3 equations, 3 unknown, that's good. But if we check our units, we have a problem here. So instead of defining this, if we know this variable is actually in meters, we can multiply it by this convert function, which converts from millimeters to millimeters, and we can check our units. And it sees that A and B differ by a factor of 1,000 because B is in meters, but we've converted it here, so it will multiply it. So this is a very handy tool if you accidentally make a mistake. Check your units and you can fix it. Okay, so either you need to multiply by the correction factor or make sure you enter the right units. If you check it here, then you should be able to get that. So if we can solve it here, we have A is in millimeters, B in millimeters, and C is in millimeters. Okay, so it says check units. There's a potential unit problem because C has not been given units. Okay, so we can go here and we can fix that by looking at this variable menu here, and we can make the units millimeters and hit OK. And then if we solve it again, still we have a potential unit problem. Dimensions are inconsistent, although the units are all correct. And we can solve it like this. Okay, potential unit problem. So this is actually not a problem because 5 is a constant, and it's not been given a unit. So if we go here and we put this in millimeters, I don't know if we can do this on the right side of the assignment. We're going to try and then run it again. Then we have no unit problems here, and we can see that there is no unit problems detected. So EES can be kind of a pain in the neck when you're first getting started, but it will save you a headache later on down the road. So I highly encourage you to use it. Now, what we're going to do is talk through the example in the book, and I'm just going to pause and stop the video here, and we'll start another video for the rest of that.